tiny flash, no muzzle smoke, no report, just a metal slug punching through armor at hypersonic speed. Imagine a shoulder-fired railgun, compact enough for a squad to carry, that fires electromagnetic rounds with surgical precision. Sounds like a comic book weapon, but advances in capacitors, rail materials, and power density are drawing that nightmare into the lab. Railguns have been the domain of big ships and test ranges. 2 conductive rails, a massive current, and a projectile that reaches incredible velocity by electromagnetic force. Shrinking that system into a pocket form changes the game. Suddenly, lethality is quiet, signatures are low, and logistics shift from chemical propellants to pure electricity. This piece breaks down the engineering, the prototypes, the ethics, and the battlefield that a pocket railgun would remake. How a railgun works. A conventional firearm uses explosive propellant to push around through a barrel. A railgun replaces chemistry with physics. An armature, the slug, bridges 2 parallel rails. When current surges through the rails, Lorentz forces accelerate the armature forward along the rails, creating velocities far beyond conventional guns. On naval scales, railguns have launched projectiles at Mach 6+. Scaling down requires 3 things: rails that survive massive current and wear, power systems that deliver huge bursts in tiny spaces, and cooling/insulation that prevents meltdown. Each of these is a technical mountain, but recent material science and capacitor breakthroughs make the climb less impossible. Power and capacitors. The heart of a pocket railgun is energy storage. Traditional capacitors are bulky. Modern supercapacitors and solid-state pulse power systems are changing that. Lithium batteries can't deliver the instantaneous power spikes needed, but ultracapacitors can. Companies are building compact banks that can discharge in milliseconds, producing the current surge to accelerate a slug. Advanced pulse-forming networks shape current peaks to optimize acceleration while minimizing rail wear. Combine that with graphene-coated rails and copper alloys, and you get a system that can fire multiple rounds before a cooldown cycle. Thermal management matters. Each shot dumps joules as heat, so heat sinks. Phase change materials and active cooling channels are woven into the chassis design. Projectile design and materials. Railgun rounds differ from bullets. Without propellant, slugs are simpler. Dense tungsten or depleted uranium penetrators, often sabot stabilized for flight. For a pocket railgun, aerodynamic shaping, sabot separation, and guidance become critical at hypersonic speeds. Materials face extreme shear and heating on muzzle exit. Ceramics, tungsten composites, and ablative coatings protect rounds long enough to reach targets. Smart projectiles are possible. Embed guidance fins, microelectronics, or reactive materials that explode on impact. Because railguns impart kinetic energy so efficiently, even small slugs become lethal anti-armor rounds. Recoil and handling. A major myth, railguns have zero recoil. Not true. Newton's laws still apply, but electromagnetic launchers can shape force delivery, spreading pulse over milliseconds to reduce peak recoil. Recoil mitigation systems, telescoping stocks, countermass systems, and active gyroscopic stabilization make a shoulder-fired railgun controllable. Design choices trade rate of fire for recoil management and size for portability. Signature and stealth. One of the pocket railgun's terrifying advantages is low acoustic and thermal signature. No propellant flash, no plume, and minimal muzzle blast mean shots are hard to detect acoustically or optically. The main signature is electromagnetic, a brief, intense current draw that can be masked with onboard capacitors and pulse shaping. For special ops, a weapon that leaves the battlefield without the telltale flash or smoke is a strategic leap. prototypes and research. Multiple labs have demonstrated scaled railguns and compact pulsed power systems. Naval railgun projects prove the concept at long ranges. University researchers and defense startups test compact coils and capacitor banks in labs. A handful of corporations demo pulsed electromagnetic launchers small enough for experimental shoulder mounts, but they are fragile, inefficient, and need rapid cooling. The next decade's breakthroughs in solid-state switching and energy density will determine if a true pocket system moves from bench to battlefield. Ethics, proliferation, and law. A quiet, armor-piercing shoulder weapon is a policy nightmare. Existing arms control treaties target chemical, biological, and nuclear weapons, but electromagnetic launchers cross legal gray zones. Proliferation risk is real. Once capacitor tech and advanced alloys spread, clandestine groups could cobble lethal launchers from stolen components. The silent nature also blurs accountability. Forensic trails vanish without powder residue. Regulators will face pressure to control materials, impose export bans, and mandate electronic locks. Militaries may seek them for precision raids, but international law and human rights groups will scream over deniability and civilian harm. Tactical impact. On the battlefield, pocket railguns reframe engagements. Infantry could penetrate advanced armor without rockets. Snipers could engage with hypervelocity rounds that defeat reactive armor. Urban warfare changes. A single shot can punch through barriers silently, empowering small unit tactics and covert strikes. Defenders would need novel countermeasures, EM shielding, active rail damping, or energy sensing networks to detect pulse signatures before an attack. Countermeasures and defense. Defending against pocket railguns forces new armor and sensors. Reactive composite layers that shatter incoming slugs, electromagnetic dampers that absorb pulse energy, and distributed sensor networks to detect pre-shot current spikes will become priorities. Urban deployments may add hardened shelters and power buffers that create decoy loads. Militaries will develop quick deploy shielding and active jamming to scramble capacitor timing. These defenses are possible, but they add cost, complexity, and arms race escalation. Still, no single countermeasure is foolproof. Layered defense combining materials, science, electronic detection, and tactical doctrine will be required to blunt the silent slug's advantage, inevitably. The railgun shrinks, the battlefield rewrites. With one quiet pulse, a minute package of metal becomes a city-busting force. For better or worse, the pocket railgun embodies the future of kinetic stealth, efficient, silent, and brutally decisive. It won't scream. It won't flash. It will simply arrive. A slug of physics that proves silence can be the deadliest sound.